बिस्मिल्लाहिर्रहमानिर्रहीम। वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिजिक्स। आज हम इसका लेक्चर नंबर 13 पढ़ेंगे। लेट्स सी व्हाट वी डिड इन लास्ट लेक्चर. So review of the last lecture, we studied Fourier series. Before that we studied periodic functions, determining Fourier coefficients, and then we studied Fourier series for even and odd functions. So if you recall, we studied the full series, Fourier series, and then for even and odd functions we had sine and cosine Fourier series. So in even functions you won't get sine terms, and odd functions you don't get cosine terms. So that's why they reduced to sine and cosine series. So the reason for studying the Fourier series was to study the method of separation of variables to solve partial differential equations. In solving partial differential equation we need Fourier series theory. So today we will be studying the method of separation of variables to solve partial differential equations. Alright, so this will be our outline for today's lecture. Method of separation of variables, and then we will be doing some examples. Again, if you have taken the course partial differential equation, then you must have studied this method very thoroughly. So if that is the case, then this lecture or this and next lecture will be the review of those methods. So it will not be a new thing for you guys, but if you have not studied a separation of variables method for partial differential equations, don't worry about it. We will be doing it very thoroughly. You will understand what's going on. So let's start with the method of separation of variable, what that is. Separation of variables is one of the oldest and most efficient solution techniques for a certain class of partial differential equations. It's very important to note that for a certain class, it's not applicable to all the partial differential equations. Daniel Bernoulli invented this technique in 1700s. So it's a very, very old method basically. The main idea of this technique is to reduce the given partial differential equations into number of ordinary differential equations, and then we construct the solutions of those ordinary differential equations. So first of all, method of separation of variable reduces your PDEs to ODEs, and then of course we know how to solve ODEs. It's easier to solve ODEs instead of PDEs. So we construct the solution based on those ODE solutions. So let's consider a second order homogeneous partial differential equation A star u xi. So u xi means the second derivative of u with respect to xi. U xi eta, mixed second derivative u eta eta, second derivative with respect to eta, u xi, the first derivative u eta, and then u. So basically you have u is unknown here, so u is there. The first partial derivatives are there, the second partial derivatives are there. That's why it's a second order partial differential equation. A star, B star, C star, D star, E star, F star. These are all coefficients of u eta, u xi, and all these derivatives. And these may be constants, but in general they can be functions of xi and eta. All right. Same with the case of ODEs. We know that in ODEs the coefficients can be functions of x. So here the coefficients again can be functions of your independent variables, which are xi and eta. With the following transformation, if we transform our differential equation to x and y instead of xi and eta, so let's say we have a transformation that x is given by this function of xi and eta, and y is given by another function of xi and eta, such that the Jacobian of the transformation is not equal to 0. If the Jacobian is not 0, then it's invertible transformation. Alright, so Jacobian is the determinant that contains partial x by partial xi, partial x by partial eta. Second row will contain partial y by partial xi and partial y by partial eta. So this is the notation for the Jacobian. It's basically the determinant. So this determinant will not be equal to 0. We can reduce the above partial differential equation into following canonical form. If we introduce some kind of transformation such that your Jacobian is not equal to 0, then you can reduce this equation into the canonical form. This is the canonical form. Now you have transformed A star to A of x and y, B of x and y, C of x and y. So these coefficients have become the functions of x and y, and the derivatives are also with respect to x and y, because you have transformed your variables xi eta to xy, which when a is equal to minus c is hyperbolic. If a is equal to negative c, this becomes hyperbolic equation. If a is 0 and c is 0, then this is parabolic, and if a is equal to c, this is elliptic. All right. Basically, it's c square minus 4ad. C square minus 4ad. This has to be negative, positive, and equal to 0 to be hyperbolic, parabolic, and elliptic. But it's the same thing. If a comes out to be equal to minus c, your b square minus 4ac automatically becomes positive. And if a is equal to c, then c square minus 4ad becomes negative. So it's elliptic. So similarly, if a is 0 or c is 0, then your c square minus 4ad is 0. So it becomes parabolic. We assume, now what is the method of separation of variable? This is the canonical form we got, that's not a problem. So what is the method of separation of variables? What we do is, we assume the solution uxy of this form. It's a product solution. One function depends only on x, other function depends only on y. Alright? So we basically are trying to separate the variables. Here you see x, y are mixed, but here x and y are separate variables, where x and y are respectively functions of x and y alone and are twice continuously differentiable. Why twice continuously differentiable? Because we need to solve this equation. So there are two derivatives with respect to x and two derivatives with respect to y. Alright? So if there are two derivatives with respect to x, two with respect to y, so these must have two derivatives as well, x and y. Substituting equation, the value of uxy into the equation, if I replace this value xy into your equation, this one, alright, then your equation will become uxx. The second derivative with respect to x will affect only this capital X, not y, because y depends on y, so that will not be changed. The derivative with respect to x only. So x double prime and y. Similarly here, x y double prime, x prime y, x y prime, and x y, no derivative. Where prime denotes the derivative with respect to their respective variables. If there is a prime on y, this is a derivative with respect to y. If the prime is on x, it's a derivative with respect to x. All right. Assume that we have a function phi of xy such that if we divide above equation by phi xy, we obtain this. So let's say if we have a function phi of xy such that if we divide this thing, then the coefficients reduce to only one variable. All right. So axy just becomes a1x, cxy just becomes beta1y, dxy becomes alpha 2x, exy beta 2x, and similarly these all variables. So here what is happening is you are dividing by such a function that makes all these coefficients function of only one variable. Alright, then we can easily divide by xy and obtain a separate equations. Dividing above equation again by capital XY. When I will divide by capital XY, y will be cancelled, x will be cancelled, y will be cancelled, x will be cancelled, both will be cancelled. So basically in each term either x will be cancelled or y will be cancelled. Alright, so there won't be any x or y. So here you see I got this thing, this term is only depending on x, this term only depending on y, this only on x, this only on y, and this only on x, this only on y. So each term either depends on x or depends on y. It's not depending on both the variables. Alright, so that was our basic idea, that we have to separate the variables. So if I keep all the x terms here and send all the y terms to the other side, it means we have separated the variables. The reason is on the left hand side there is no y at all, and on the right hand side there is no x at all. you are getting only small x variable on the left and small y variable on the right hand side. So basically we have separated the variables. The left hand side of the above equation is a pure function of x and the right hand side is a function of y only. Thus differentiation of above equation with respect to x yields 0. If I differentiate right hand side with respect to x, it will give me 0. So the derivative of left hand side is equal to 0. It means the left hand side has to be a constant. Similarly, if I differentiate with respect to y, left hand side will become 0 and the derivative of this is equal to 0. It means this term is also constant. You can also say that because on the left hand side we have only x variable, on the right hand side we have only y variable. So the only possibility they are equal to each other if they are equal to a constant. Otherwise they won't be equal to each other. A function of x, how can that be equal to a function of y? Only if they both are constants. Alright? So if they are equal and they have to be constant, so we can say that these both are equal to lambda. If they are equal to lambda, lambda is any constant. Alright, then I can multiply this y on the right hand side, and from here I can multiply x on the right hand side. These are the two ODEs I got. These are just ordinary differential equations, you see. This is just an equation in x, this is just an equation in y. So we are having two ordinary differential equations here. So finally we obtain the following. Ordinary differential equations, which is this is equal to this is equal to this. Alright. So here one equation is in x, one equation is in y. Both are second order ODEs, we are able to solve them. Thus the solution x uxy is the solution of the given partial differential equation if capital X and capital Y are the solutions of these ODEs. Alright, because our xy will satisfy our equation if and only if our xy satisfies these two equations. Alright, so this is basically the method of separation of variables. Now let's consider a special case where a, b, c, d are constants. If the coefficients of the given partial differential equations are constant, then the reduction to canonical form is no longer necessary. Alright, if your coefficients are all constants, then you don't worry about canonical forms. The reason is the variables will be separated without even converting them to canonical form. Alright, as before, we assume the solution of the form, which is a product solution. Replace that in your equation. Divide by axy. This will yield. Now you don't have to divide by that phi xy. Right? Over there we imposed a condition that we have to divide by a function such that the coefficients reduce to only one variable functions. But here your coefficients are already constant, so you don't need to do that. You can just divide by the product solution. So if you divide by the product solution, this is what you get. So now you can again separate the variables. So the left hand side is a function of x only, right hand side is a function of y only. So again they will be equal to a constant. If they are equal to constant, then I can put both the values equal to lambda. So if they are both equal to lambda, again we are getting two ordinary differential equations. See, one is this, one is this. So again we are getting two ordinary differential equations. So therefore uxy is the solution of the given partial differential equation if and only if x and y are the solutions of these two differential equations. Alright, so one PDE has been converted to two ODEs, then I can solve two ODEs to find the solution. Alright, so let's see now some examples of this separation of variable. How can we actually develop the solutions by using the method of separation of variables? So this is a parabolic equation. Solve the following initial boundary value problem. utxt is equal to uxxt, 0 to 1, t positive. Boundary conditions are 0 and initial condition is this. I don't know if you have seen this equation before, but this is called the heat equation. It is diffusion equation. It is also called diffusion equation. If you consider temperature or heat flow inside a one-dimensional rod, if you consider a one-dimensional rod of length 1 maybe, because x goes from 0 to 1, length 1, and it's perfectly insulated from lateral side, that if heat is flowing only from left to right, heat is not escaping the rod within 0 to 1. So if you model that heat equation, if you model the flow of the heat, then the temperature at any point is given by this equation, heat equation. Here the temperature at the ends is 0 and the initial temperature is given by 2x plus 1. So let's solve this. So our example is ut is equal to uxx. Right? X goes from 0 to 1 and t is positive. Boundary conditions are that u0t is equal to 0 and u at 1t is also equal to 0 for t positive, and u x0, the initial condition is 2x plus 1 and x between 0 and 1. So as I was mentioning, this is basically the application of the heat flow in a one-dimensional rod. Let's say this is a one-dimensional rod, a homogeneous rod of length 1, 0 to 1. All right. Let's say u at any point x, this uxt gives you the temperature. All right. Because heat is flowing, so of course temperature is changing at any point and for any time t. All right. So this is basically heat is flowing from left to right. So if you model the heat flow inside a one-dimensional rod, which is perfectly insulated from the lateral sides, that no heat is escaping or entering from the sides. All right. So now the conditions which we imposed here, there can be different conditions, but the conditions which we imposed is that at the left-hand side it is 0, at the right-hand side is also 0. So we are not giving any temperature at the ends. Only that is, initially the temperature was given by 2x plus 1. That's why heat is there. All right. So this gives you basically the basic phenomena of heat flow inside the one-dimensional rod of unit length. So if I use the separation of variable method, if I use the method of separation of variables, what we do is we assume the solution of the form uxy is equal, uxt is equal to x of x, and second variable is t, so I can take capital T of t. This is your choice. You can call f and g. It's not a hard and fast rule to name them capital X and capital T. You can call it f, g, phi, g, whatever you want. You can do that, right? In many books, I think the book which I mentioned of Haberman, this is the notation which Shankara Rao uses in his book, and if you see the Haberman's book, he uses this. He uses phi for x and capital G for t, or sometime h for t. All right. So this is your choice, whatever you want. All right. It's not necessary. So now our PDE, this PDE 1, let's call it 1, right? So therefore, PDE 1 becomes ut means x as it is the derivative of time, and uxx means the second derivative of x and t as it is, right? Now if you divide by, as we mentioned, it's a constant equation with a constant coefficient, so we can directly divide by xt. If there is a constant, we will divide by that constant too, but there was no constant. So if divide by xt, we obtain xt prime over xt and x double prime t over xt. So see here, x is gone and here t is gone. This t is gone, here x is gone. So you got t prime by t and x double prime by x. So t prime by t and x double prime by x. So now you see on the left hand side we have small t only. These both are the functions of small t, and these are both the functions of small x. All right. So that's why they should be equal to a constant. You can call it lambda, minus lambda, whatever. We take this minus for our convenience. There is nothing, you can even take lambda, doesn't matter, but for convenience we take negative lambda. It looks a little better. How it looks better you will come to know in a second. Now t prime by t will be equal to minus lambda, x double prime by x should be equal to minus lambda. So here you will get x double prime is equal to minus lambda, and you bring it here, so it will become plus. So just here now you see it looks better that x double prime plus lambda x equal to 0, and t prime plus lambda t equal to 0. But it will not make any difference if you take this to be a plus lambda. Then you will get minus sign here, nothing changes. It's still a differential equation. So we got these two differential equations to be solved. And now we had some conditions as well. See, uxt, u1t is equal to 0. So if u0t is equal to 0, means x at 0 and capital T at t is equal to 0. What is u0t? u0t will become x at 0 and capital T at t. Now one of them has to be equal to 0, and that should be this one, because this is a constant. X at 0 should be a constant, and this is a variable t of t. Now if capital T of t is 0, then this whole solution will become 0, but we are looking for non-trivial solutions. Alright, so that's why this is not the possibility. T of t cannot be equal to 0 identically. Alright, because otherwise, if it is 0, then otherwise your solution will become 0, and we are not interested in that. Right? We are not interested in 0 solutions. That's why we cannot take this capital T of t is equal to 0. But x at 0 can be equal to 0. This is not the whole x. This is x, the value of x at some point may be 0. No problem, right? So this is one of the conditions. What is the second one? That u of 1t is equal to 0. Again, it is x at 1 and capital T at t is equal to 0. So this will again imply that x at 1 can be equal to 0, but t at all values of t cannot be equal to 0. So these are the two conditions along with it. From third equation you will not get anything. This is not a homogeneous condition. ux0 to x plus 1. So we will keep it for later. ux0 initial condition is equal to 2x plus 1. Keep it for later. We will use it later on, but we cannot do anything with that. The reason is, if you want to split it, this will become x of x and t of 0 is equal to 2x plus 1. So again, what can I say about this? What can I say about t of 0? I don't know. Right? Because we don't know what our x is. So that's why t of 0 is unknown here, so I cannot use it. So that's why we said keep it for later. Alright? So right now we have this thing. So we have a boundary value problem, which is x double prime plus lambda x equal to 0, along with the conditions x0 is equal to 0 and x1 is equal to 0. So this is our one of the boundary value problem, and an ordinary differential equation without initial condition, this one. So I have these two things. So from here it's very easy to find the solution, because it is t prime by t is equal to minus lambda. So if you integrate, it is log of t is equal to minus lambda t plus constant. So your t from here is constant times e to the minus lambda t. Alright? So this is one, I got this solution for t. But here I need to solve the boundary value problem. Here doesn't matter what lambda is, your solution is fixed. But here it will matter. Here for different values of lambda, you will be getting different solutions. Right? Now we solve boundary value problem, let's call it star, let's say boundary value problem star for 3 different cases for lambda. That is lambda 0, lambda negative and lambda positive. So these are three cases. What will happen if lambda is 0? What will happen if lambda is positive? And what will happen if lambda is negative? So these are the three cases. So first let's start with case 1. Case 1 is lambda is equal to 0. If lambda is equal to 0, then our equation is x double prime equal to 0, right? This lambda is 0, then this term drops out. So from here x is equal to c1x plus c2. Now if you use the conditions, x0 is equal to 0 will make it c10 plus c2 is equal to 0. So this implies that c2 is equal to 0. Now x becomes just c1x. Now if you use the second boundary condition, x1 is equal to 0, it means c at 1 is equal to 0. So this implies c1 is also equal to 0. So this implies capital F of x is identically equal to 0. So it's a trivial solution. And we don't need that. We don't need trivial solutions. I need non-trivial solution. The value of lambda that gives non-trivial solution is called the eigenvalue of this system. All right? The value of lambda for which we get non-trivial solution, because we are only interested in non-trivial solutions. So it means we are only interested in eigenvalues. Non-trivial solutions, the value of lambda for which we get non-trivial solution is called an eigenvalue for the problem. You remember in the integral equations, we also define eigenvalues, eigenvectors, eigenvalues, eigenfunctions. The value which gives you non-trivial solution for the linear system was called eigenvalue. All right, and eigenfunctions were non-trivial. So this implies that lambda is equal to 0 is not an eigenvalue, because it gives me only the trivial solution. Right? It gives me trivial solution, so it means lambda is equal to 0. So this case fails. I will not consider lambda is equal to 0 again. Now case 2. Lambda negative, let's say. If lambda is negative, you can write x square plus x is equal to 0. Auxiliary equation is m square plus lambda is equal to 0. M square is equal to minus lambda. Since lambda is negative, and minus lambda will become positive. All right? If it is positive, you can call it alpha square, say. Because plus alpha square is always positive number. So it's easy to remember that now it's positive. So we can call it alpha square. So from here, m becomes plus and minus alpha. So therefore, what is your solution? X of x. This is c1 e to the alpha x plus c2 e to the minus alpha. When you get real and distinct roots, real and different roots, this is your solution, right? For the second order homogeneous equation. So now, using boundary conditions, x at 0 is equal to 0 implies that c1 plus c2 is equal to 0. X at 1 is equal to 0 implies that c1 e alpha plus c2 e minus alpha equal to 0. From first equation, your c2 is equal to minus c1. So here, if I replace c2 with minus c1, this is what I get, right? I replace this value here. So this implies this one, since c2 is equal to negative c1. I replaced it here. Now c1 is constant, so e alpha minus e minus alpha is equal to 0. Now you see, c1 and c2 are equal. If c1 is equal to 0, then c2 will become 0, and this whole solution will become 0. As we know that we are not interested in 0 solutions, so I have to make c1 not equal to 0. At least I will try, right? So for non-trivial solutions, c1 has to be not equal to 0. So this implies that e alpha minus e to the minus alpha should be equal to 0, right? So e alpha should be equal to e to the minus alpha. If you divide, you will get e to the 2 alpha is equal to 1, and if you take the log, 2 alpha will become 0. So this implies alpha is equal to 0. So if alpha is equal to 0, this implies lambda is equal to 0, which is not true. Which is not true because lambda was negative. This is not true because lambda was negative. It was not equal to 0. So it means we got the contradiction. So we got a contradiction. It means this is not true. this cannot be equal to 0. Alright, so contradiction, this implies that E alpha minus E to the minus alpha cannot be equal to 0. So this implies that your C1 has to be equal to 0. If C1 equal to 0, then C2 is also 0, and this implies that your X is again identically equal to 0. Again we got the trivial solution. We tried to get non-trivial solution, but we were not able to get it. We were unsuccessful. So therefore lambda less than is equal to 0 is not an eigenvalue too. Alright, so we did not get any non-trivial solution for lambda negative, so this is also not an eigenvalue. So I will remove this case as well, that lambda cannot be 0, lambda cannot be negative. So now only possibility is lambda can be positive. So let's discuss that. So we expect, of course, one of them should be true. So lambda positive case. So if lambda is positive, then auxiliary equation is this: m square is equal to negative lambda. So if lambda is positive, then I can call it minus alpha square, because alpha square is always positive and minus will make it negative. Right? So this is now always negative. Lambda positive, negative will make it negative. So m is plus minus iota alpha now. Alright? Iota alpha means your x is C1 cosine alpha x plus C2 sine alpha x. Right? Whenever you get pure imaginary with alpha as your imaginary part, then this is your solution. Now x at 0 is equal to 0 implies that C1 cosine 0 1 plus C2 sine 0 0. So this is 0 implies that C1 equal to 0. If C1 is equal to 0, your x will become C2 sine alpha x. Alright. Now use the second condition. X1 is equal to 0. It means C2 sine alpha and x is 1 equal to 0. Now again C2 cannot be equal to 0 for non-trivial solution. Again I am trying my best to get non-trivial solution. So for non-trivial solutions, it's important that C2 has to be non-zero. So if C2 is non-zero, then sine alpha has to be equal to 0, and this is possible, no problem. Sine alpha can be 0 when alpha is n pi, right, where n is 1, 2, 3, so on. Alright, so what is alpha? Alpha was square root of lambda, right? Here, what is alpha? Alpha is square root of lambda, because lambda is alpha square. Alright, lambda is alpha square. So square root of lambda is n pi. So lambda, the eigenvalues I got for non-trivial solutions are n square pi square, where n goes from 1 to 3. I did not take the negative because sine negative n pi is also 0, but here lambda was positive. I am considering the case lambda positive. Lambda is positive, that's why I only took n goes from 1, 2, 3, 4, not negative or 0. Even 0 I cannot include. Sine 0 is 0, but alpha is not 0 in this case. Alright, so these are the eigenvalues, and it means C2 is arbitrary in this case. So this implies C2 is arbitrary. I can take any value of C2. So therefore x of x is C2 sine alpha x, and the value of alpha is n pi. So sine n pi x, right? Sine alpha x. So alpha is n pi. So this is my solution. These are your eigenfunctions. So this implies that lambda is equal to n pi square, and x is equal to sine n pi x. These are the eigenvalues and eigenfunctions respectively. So these are eigenvalues and eigenfunctions. Alright, so finally we got eigenvalues and eigenfunctions. So this is what we got. So therefore, what will be our product solution now? Therefore the product solution will be is uxy is equal to x of x and y and t of t, not xy, not xy, it's xt. Xt is x. So what is x of x? X of x is sine n pi x, and t was e to the minus lambda t. right? What was t, if you recall? T was this, c constant times e to the minus lambda t. And what is lambda now? I can replace the value of lambda. Lambda is n pi square t. All right? N constant, you can write it up front. So this is your product solution. Now the problem is, this is not just one solution. This is the solution for all n goes from 1 to 3 up to infinity. So these are infinite many solutions. So if these are infinite many solution, for every n it is a different solution. So I can, so these are infinite many solutions. One for each n, right? One for each n, and 1 and 2 and 3. So it is better to introduce a subscript for uxy and write unxy is equal to constant, and I can, the constants will be different as well. So sine n pi x e to the power minus n pi square t. Because for every n it is different, so I can call it u1, u2, u3 instead of u all the time. Alright, so for n is equal to 1, it is c1 sine pi x e to the minus pi square t, which is u1. For n is equal to 2, it is u2, which is c2 sine 2 pi x e to the minus 4 pi square t, and so on. Alright, so these are all solutions. Now, according to the principle of superposition, if u1, u2, so on are solutions of a homogeneous partial differential equations, then so is u1 plus u2 plus so on. If you have 2 or 3 solutions of homogeneous partial differential equation, then their sum is also the solution. Alright, so we can use this principle of superposition to construct the general solution. So therefore, the general solution of the given PDE is, the general solution of the PDE is uxt. Uxt is basically the sum over all the values of u and xt. This is the principle of superposition. If you have more than one solutions, then their sum is also a solution. Not just sum, linear combination, you can introduce constants as well. But we have already written down the constants with un, that's why I'm not writing it. So Cn sine n pi x e to the minus n pi square t. So this is your general solution of the partial differential equation. Right, where Cn are arbitrary constants and can be determined by the initial condition. If you recall, we haven't used the initial condition yet. You see, at the beginning, we said keep this for later. We haven't used this initial condition. I said keep it for later. And now it is time to use it. Right? We haven't used this boundary initial condition yet. So now I can use the initial condition. So if I use the initial condition ux0 is equal to 2x plus 1, then what is ux0? 2x plus 1 is equal to, ux0 is Cn sine n pi x, and e to the 0 is 1. Because t is 0, so e to the 0 is 1. So this is what I get. Alright? The right hand side is what? This right hand side is the Fourier sine. Isn't that? Right hand side is the Fourier sine series, and this is equal to the function 2x plus 1. And we know how to obtain the coefficients of this equation. Right? We know how to obtain the coefficients. So therefore, so this implies that Cn are the Fourier coefficients basically. Fourier coefficients, and can be determined by the following formula. By the formula, we remember from last lecture, what was the formula for Cn? If we have Fourier sine series, right, fx sine n pi by L x dx. Alright, but in our case, L is 1 and fx is 2x plus 1. So our Cn is nothing but 2 by L. So 2 by 1, 0 to 1, fx is 2x plus 1, 2x plus 1, and sine n pi x, because L is 1, dx. So if you integrate, you will be able to find Cn, and that will be your solution. So this is 2 times by parts, 2x plus 1 as it is, sine has integral minus cosine by n pi, 0 to 1, and minus 0 to 1. The derivative is 2, and minus cosine n pi x by n pi dx. So here if you replace 1, I will get 3, and cosine n pi by n pi. So minus 3 cosine n pi by n pi, and 0 will make it 1, and cosine 0 is 0. So plus cosine 0 is 1. So plus 1 over 2 pi. Plus 1 over 2 pi. And then minus plus 2 is outside. And cosine has derivative n pi by n pi. And 1 n pi was already there. So it is square from 0 to 1. So this is 2 times 2 by n pi. If I take 1 by n pi common, so this is 1 minus 3 cosine n pi, and plus sine n pi is 0 and sine 0 is 0, so this is 0. So all I got is 2 times 1 minus 3 cosine n pi divided by n pi. Hence our solution is, hence the final form of the solution is uxt is equal to summation n goes from 1 to infinity. Cn comes out to be this one, and sine n pi x e to the minus n pi square t. So this is the final solution of our given partial differential equations with the given boundary and initial conditions. So this is what we get at the end. It's a little lengthy process, method of separation of variables, but it gives you precise, exact solution of the differential equation, which is very good. Alright? So this is what you got. So step by step, let's recall it again. Step by step. First of all, you assume the solution of the form, this product solution, replaced it, divided by xt to get these variables separated. After getting this, you can call it plus lambda or minus lambda, it's your choice. In practice, we take minus lambda. So I got one ODE and one second order ODE. By using boundary conditions, I got conditions on this equation, not on this one. I got conditions on this equation. So x0 and x0. So this is our boundary value problem, and this is alone. So I got one boundary value problem, which is star, and one ODE. ODE, the solution of the ODE is straightforward, I found that. But lambda is not known here. So from this boundary value problem, this is also called eigenvalue problem. Alright, this is sometimes called eigenvalue problem. So eigenvalue is the value of lambda for which your solution is non-trivial, non-zero. So we considered 3 cases. For lambda 0, I got trivial solution, so it means lambda 0 is not an eigenvalue. For lambda negative, again we got the trivial solution. We got the trivial solution, so again lambda negative is not an eigenvalue either. So lambda positive gives me the, because non-trivial solutions, so it means I got some eigenvalues and eigenfunctions there. So these are eigenvalues, these are eigenfunctions. After getting these eigenvalues and eigenfunctions, I wrote the product solution. Because product solution is not just one, these are different solutions for different values of n, so we introduced a subscript here. So the product solution, you can directly write this. You don't have to write this first. You can directly write this product solution as un and write that coefficient as cn as well. So these are the infinite many solutions. By using the principle of superposition, we said the sum of all these solutions will be your general solution. And here cn are still unknown coefficients, but I was left with one initial condition. I used that initial condition. I got a Fourier series, and now we studied the whole lecture, previous lecture, studying this Fourier series. I can easily find the values of cn to get the answer. Alright? Alright, so second example in that slide was again the same differential equation, heat equation, uxx, ut is equal to uxx. From 0 to 1, t is positive. Boundary conditions are changed now. Instead of u1t, we can write ux at 0t is equal to 0 and ux at 1t. Means an initial condition can be anything. ux0 is equal to fx. I think x square is there. So you can even solve it for general f of x. So now you see, instead of taking the prescribed temperature, we took the derivative at 0. So before that, at 0 and 1, we had u0. U was 0, u was 0. It means the prescribed temperature. At the ends, there is 0 temperature. But when we take ux equal to 0 at the end, it means the ends are insulated. Always remember, when the derivative is 0, partial u by partial x is 0, means the end is insulated. What do we mean by insulated? Means there is perfect insulation, no heat can enter or escape from this end. Similarly, no heat can enter or escape from this end. Insulation means that. Alright? So here we took the temperature distribution in a uniform rod, one-dimensional rod with insulated ends. This is the physical description of this problem. So again, solution is same. I will leave many things for you in this example, just because it's very similar to what we did earlier. So again, if I assume the solution of the form, you can fulfill the details. So assume the solution of the form uxt is equal to capital XX and capital TT. Alright, so again, our PDE will become xt prime x double prime t. Again, if I divide by xt, I will get x cancelled on the left hand side, and I will get t cancelled on the right hand side. So 1 is a function of t, 1 is a function of x equal to minus lambda. So again, your equations will become t plus lambda t is equal to 0. This will have a solution. Again, I don't have to really discuss it because we just solved it in the previous example. And then x double prime plus lambda x equal to 0. This depends on the values of lambda. Now, boundary conditions, instead of now I have ux at 0, t is equal to 0. It means x prime at 0 and t of t is equal to 0. So again, t of t cannot be equal to 0, so x prime has to be equal to 0. Second is ux at 1 t is equal to 0. So it means x prime at 1 and t at t is equal to 0. So x prime at 1 is equal to 0. So the boundary value problem that I got is x double prime plus lambda x is equal to 0 with x prime at 0 is equal to 0 and x prime at 1. So see, only difference between this one and the previous one is that we have the same equation, but the conditions were x at 0 is equal to 0 and x at 1. Now the derivatives are 0. Now the derivatives are equal to 0. So solutions again remain the same, lambda negative, positive, 0. We will discuss all the cases here. So case 1, lambda is equal to 0, gives you x double prime equal to 0. So this means x is equal to c1x plus c2. Now x prime is just c1. So both the conditions gives you c1 equal to 0. See, if x prime at 0 is equal to 0, this makes c1 is equal to 0. All right. So this implies that your x of x becomes just c2. And now x prime of x is already 0. So it means x prime at 1 is automatically equal to 0. This is fine. So x of x is equal to c2. C2 is arbitrary. So it means I am not getting a 0 solution for 0 case. So lambda is equal to 0 is an eigenvalue. This implies that lambda is equal to, so it means lambda equal to 0 is an eigenvalue. So see, in the previous case lambda 0 was not an eigenvalue, but in this case lambda is equal to 0 is an eigenvalue. Alright, so now case 2, lambda negative m square is equal to minus lambda. So if lambda is negative minus lambda is positive, I can call it alpha square. So it means m is plus minus alpha. So again your x becomes c1 e to the alpha x plus c2 e to the minus alpha x. So if x, now if you take x prime, this is c1 alpha e to the alpha x minus c2 alpha e to the minus alpha x. So I have to impose conditions on derivative. So x prime at 0 is c1 alpha minus c2 alpha is equal to 0. So again from here c1 is equal to c2. X prime at 1 is equal to c1 alpha e to the alpha minus c2 alpha e to the alpha minus alpha is equal to 0. This implies that c1 and c2 are equal. So I can take c1 as common and alpha is also common. So e to the alpha minus e to the minus alpha is equal to 0. Yeah, if we go back to the previous example, what we had here is again the same thing exactly. You see, because over there c2 was equal to minus c1, so I got e alpha minus e to the minus alpha. And now because of the derivative, now if you see c1 and c2 are equal, but because of the derivative I got a minus sign here. So now again alpha is not 0 because alpha is negative. So this alpha is not equal to 0, of course. And c1 cannot be equal to 0 because if c1 is 0 then c2 is 0 and the whole solution will become 0. So only possibility is e to the alpha minus e to the minus alpha is equal to 0, right, for non-trivial solution. For non-trivial solution this should be the case. But from here I know that this is not possible because if you send it there, divide it, I got e to the 2 alpha is 1 and 2 alpha is equal to 0. It means alpha is equal to 0. Not true, because alpha was not equal to 0. So it means that lambda negative gives the trivial solution only. It means I will not give non-trivial solution. So this will give you only the trivial solution. So now case 3. So this is the same case. In previous example lambda negative was not an eigenvalue, and here lambda negative is again not an eigenvalue. So let's move on to lambda positive case. So if lambda is positive, I can take m square is equal to minus lambda, so I can call it minus alpha square where alpha is not equal to 0. So your roots become plus minus iota alpha. So x is c1 cosine alpha x plus c2 sine alpha x. And now take the derivative because our conditions are on the derivative. So x prime are minus c1 alpha sine alpha x and plus c2 alpha cosine alpha x. Now if I use the conditions, x prime at 0 is equal to sine 0 0 cos 0 1. So this is c2, this is equal to 0. So your solution becomes c1 cosine alpha x. This is your solution. Now the derivative is minus c1 alpha sine alpha x, and now use the second condition here. X prime at 1 is equal to 0 implies x prime of 1 means minus c1 alpha sine alpha is equal to 0, because x is 1, so sine alpha. Again, C1 cannot be 0, alpha is not equal to 0, so only possibility is that sine alpha is equal to 0, and this is the possibility for non-trivial solutions. For non-trivial solution, this should be the case, and again alpha becomes n pi, all right, and goes from 1 to so on. So this implies that lambda is, which is alpha square, all right, so that is n pi square. Same eigenvalues. I got same eigenvalues, but eigenfunctions are the different. Xx are constant times cosine alpha x, n pi x. Right? What is your x? X is cosine alpha x. So you see, you got different. Eigenfunctions are different in this case, but eigenvalues are the same. So therefore, the product solution is, I got x and I got t. Therefore, the product solution is, and now I can directly write product solution as unxt instead of writing xt, and I can call the coefficient cn as well, cosine n pi x, and e to the minus lambda t, and lambda is n pi square t. So this is the only difference. See, this is the only difference between the previous and one. So by the principle of superposition, I can write the general solution as, by the principle of superposition, the general solution is uxt is equal to sum of all un xt, and that is cn cosine n pi x e to the minus n pi square t. So this is your solution. And now we had one more solution as well. If you recall, this is the solution for n is equal to 1, 2, 3, so on. But we had this 0 solution as well. 0 was also an eigenvalue, and constant was the eigenfunction. All right? So it means I have a constant here as well. So I can call it C naught. So I have a constant here as well. I can call it U naught xt. Right? That came from lambda equal to 0 case. So this only gives me, x was constant here, C2, and e to the power minus lambda was 0t, so it's just a constant. So I can call it C naught maybe, because I'm calling C1, C2, C3, so on. So I can call it C naught. So it is C naught plus this. But if you want to write the whole series, I can call it C naught by 2. I can call it C naught by 2. The reason, if you recall the Fourier, cosine series in your last lecture, we call this constant to be C naught divided by 2, not just C naught. Right? So this is a constant solution, and plus so on. And if you don't want to write 2, you can start it from 0 to infinity, and this will give you the same thing as well. All right? So now use the initial condition to find C naught and Cn. So if you use the initial condition, which is ux0 is equal to x square. I guess this was the initial condition. I can go back and see in this example. Yes. Yeah, here. Initial condition is x square, which we keep it for the end, and now there is the end, so I can use it. So ux0 is C naught by 2 infinity Cn cosine n pi by x, and e to the power 0 is 1. This is equal to x square. So x square is an even function, you see. X square, even function. And on the left hand side we have only Fourier cosine series. Right? We know that for even function cosine series, we can obtain the coefficients. So C naught and Cn are obtained as C naught is equal to, it was I guess 2 by L0 to L fx dx, right? So L is 1 here, so L is 1, fx is x square dx. So that is 2 times x cubed by 3 from 0 to 1. So it is 2 by 3. And similarly, Cn is 2 by L, 0 to L, and fx sine, cosine, sorry. It's a cosine series, so cosine n pi by xl. So L is 1 and fx is x square. So now I can use integration by parts twice. X square as it is, sine has integral cos n pi x by n pi, 0 to 1, minus 0 to 1. X square has derivative 2x and minus cosine n pi x by n pi dx. All right. So here if I replace 1, I will get minus cosine n pi by n pi. But if you replace 0, this x square will make it 0. So I get minus cosine n pi by n pi. Minus 2 cosine n pi by n pi. Here this is minus, minus plus, and this is 2. So 2 times 2 is 4. 4 by n pi is outside and x cosine x inside. 4 by n pi is outside, 0 to 1, and you are left with x cosine n pi x. So again I need to use integration by parts. All right. So this is minus 2 cosine n pi by n pi plus 4 by n pi. X as it is, cosine has integral sine n pi x by n pi from 0 to 1, and 0 to 1 x is 1 and sine n pi x by n pi dx. And now this is 0 because sine is 0. Sine at n pi is 0 and sine is 0 as 0, so this is gone. No contribution from here. Minus 4 by n pi square. And now integral of sine is again minus cosine n pi x by n pi from 0 to 1. And this is minus, minus plus 4 by n pi cube cosine n pi minus 1. So this is your constant. All right, so I got the complete solutions now. So therefore, the general solution uxt is c naught by 2, c naught is 2 by 3. So 2 by 3 by 2 is 1 by 3 plus summation n goes from 1 to infinity Cn. If you want, you can write Cn together. This is your Cn. Cn cosine n pi x and e to the power minus n pi square t. So this is your general solution of the given partial differential equation with boundary conditions and one initial condition. All right. So that's how. So I explicitly did 2 examples, very precise and very detailed 2 examples, which uses the method of separation of variables. Of course, it's not very difficult, just a little bit of work. With little bit of practice, you will master this technique. All right, so these were the 2 examples which we just solved. These both are the examples for the parabolic equation, and parabolic equation is basically heat equation in this case. In both the example, we considered the diffusion or heat equation with different boundary conditions. All right, so I'm leaving one example for you guys at the end here. You see, this is again a parabolic equation, again a heat equation, but now the conditions are different. Boundary conditions are a little different. You see, u at minus 1 is the same as u1, and u at minus 1 is the same as u. So at 1 and at minus 1, your temperature is the same, and at 1 and at minus 1, your derivative is the same. So this is going from minus 1 to 1 instead of 0 to 1. All right, so this goes from minus 1 to 1 instead of, sorry, 0 to 1, yes. So try this problem. I hope you will be able to solve it completely. I will continue with the same method of separation of variables in next lecture, and we will be solving wave equation, another very special partial differential equation and a very basic partial differential equation. There are three classical partial differential equations. One is heat equation, wave equation, and Laplace equation. So these are very basic three partial differential equations. We can apply method of separation of variables to any of the equations. Today we solved a couple of heat equations with different boundary value problems. I left one heat equation with different boundary conditions for you guys. I will be doing wave equation. I will be solving wave equation with the same method in the next lecture. So today we studied method of separation of variables and did a few examples as well. Next time I will continue with the same method, and we will do examples from the different kind of partial differential equation. And with this, I thank you very much for being with me. I hope you understood what we learned today. I'll see you next time. Till then, Allah Hafiz and Assalamu Alaikum.